Testing.
Hello,
Hi, Syed. Morning.
how are you?
Not too bad. What about you?
Not bad.
Okay, let's let everyone through.
I don't seem to be able to see the
Oh,
waiting
right.
group.
Sorry.
Ah, okay, there we go.
Morning, everyone. All right. All right. So I'm going to leave questions till the end or in the middle, but not. Let's not start with questions. I just want to make sure that I open up with this this idea here of composition of linear maps. So this is a really key idea, and it has to do with matrix multiplication. So matrix multiplication is probably the most important operation that you learn in linear algebra. Um, it's fundamental for many types of computations all over math and physics, but it really comes from this idea of linear maps. So just let me just remind you that we've been studying linear maps, which are the morphisms for vector spaces. So if you have two vector spaces over the same field, then you can have a linear map between them. So let's say that we have V and W are vector spaces, let's say finite dimensional vector spaces over the field over F, let's say. And suppose that we have a linear map T from V to W. Okay, so remember that the key thing about these linear maps is that because of the fact that they send sums to sums and they send scalar products to scalar products, yeah, that's the definition of a linear map. Because of that fact, once you know the value of T on a basis of V, you can figure out its value on any other vector, because all you need to do is take your vector, expand it in terms of the basis, apply the linear map, and then you know that because the vector is a sum of scalar multiples of the basis, you can express the result as the sum of the scalar multiples of t applied to the basis. So, so in other words, when you need to learn how to cook, right, all you need to do is to learn how to cook each recipe in the cookbook. And then if someone asks you for, 5 cookies, 15 muffins, and 3 cakes, you already know what you need to know. You just need to apply linearity. You need to apply the linear map to each one, and depending on how many they ask for, you apply it several times and so on. Okay, so so matrices are exactly matrices. They kind of encode this whole idea. Matrices express the fact that although the map T is acting on infinitely many vectors potentially, you only need finite amount of information in order to encode T. So how do we do that? So the matrix of the linear map T relative to, so in the bases, let's see, I'll choose bases now. So let me call beta V1 up to Vn. Let's assume that this is a basis for V. And let's assume that gamma, which is W1 up to WK, is a basis for W. So once I've chosen bases, then what I need to do to determine the matrix, so the matrix of T, you could put a square bracket in front, but it's maybe not so, it's not so important. You could write this in the following way. So I'm going to use the basis for the domain, the basis beta for the domain, and the basis gamma from the codomain. You could also write it as something like this if you really wanted to accentuate the fact that it's a matrix. But anyway, the important thing is which linear operator, what basis for the domain, and what basis for the codomain are you going to use? So you need to write that down. Okay, is a matrix like this: A11 up to AK1 up to A1n up to AKN. Okay, what are these coefficients? So where the columns show the coefficients of T applied to, let's say, V J in the basis gamma. Okay, so in other words, i.e., if I apply T to the jth basis element of the domain, what will we get? We should get A1j, the first element of the jth column, multiplied by W1, plus, going down the column, AKJ, WK. Or in other words, I can write it as the sum of AIJ WI, where I goes from 1 to K. Okay, so in other words, the entries of the matrix are determined by this formula. Okay, that's what we discussed last time. I think that in the text, they write this as the matrix of T with respect to the basis beta for the domain and gamma for the codomain. Okay, the important thing is really just to have some kind of notation that indicates what the operator is, what the domain basis, and what the codomain basis is. Okay. Now, So this is, maybe this is the first thing. This is the matrix of a linear map T. Okay, now the matrix of a vector in the domain. Let's say that we have, let's say that we have, instead of a linear map, let's suppose that we have an actual vector x inside the domain. Okay, now this vector, I can also describe it in terms of the basis. The basis for V is like this. So I'm going to write it like this. It may be a little confusing at first, but I'll explain. It's a column vector, a column matrix. We have x1 up to xn. It has to have n coefficients because it's an element of an n-dimensional vector space where x is equal to x1, v1. So I just expand it in terms of the basis. I write it as a linear combination of the basis. Okay, so why? So I hope that it's clear. Some of these things should be clear, some will not be clear. So the thing that's clear is that any vector, I can expand it in terms of a basis and describe it in terms of n numbers in the field. Here the AIs are in the field, of course. But why do I put them this way? Okay, well, the reason is that, to explain this, I'll just write, we may view any vector x in V as defining a linear map from the field into V. This is one of these fancy kind of simple ideas where the number 1 is sent to the vector x, and any other number, lambda, would be sent to lambda x. Okay, so this is a simple idea that we can actually think of vectors in a vector space as if they were linear maps from the field into the vector space. Okay, and the point is that this here, this number 1, this is the standard basis element of F. Because remember that any field is a one-dimensional vector space over itself, and it has a standard basis, which is 1. Okay, and so here in the notation, what you see is that I've written my vector V. Okay, and I'm thinking of it as if it was a vector, as if it was a linear map from the field into the vector space. Okay, and I'm not writing any notation for the basis of the field on the here because there's an obvious choice, which is just the number 1. That's the basis, and then I'm using the basis of V, which is beta. So what I'm trying to say is that this is a special case of this notation. Okay, you could say, if you wanted, that this is the matrix of X relative to the basis 1 and the basis beta. Okay, I'm just, I mean, some people might be put off by this as being too abstract or something. Why should I think of a vector in a vector space as if it was a linear map from the field into the vector space? Okay, well, you don't really have to. You just remember the fact that we are denoting vectors by column matrices by just expanding them out in terms of the basis and putting them as a matrix like that. Okay, so that's number 2. So this is number 1. Number 2, matrix of a vector. Okay, and then we can, so number 3 is that we can apply, we can apply the linear map to the vector. Okay, so I can take the linear map, I can apply it to the vector, and what will I get? I will get a vector in W. Okay, so we have a linear map from V to W. Okay, and I can take this linear map, apply it to X. That's going to push me into W, and then I can ask the question, what is the vector that I get in the basis of W? So what exactly, explicitly, is the result Tx? Okay, so what I'm saying is this: suppose that we know what X is as a vector of numbers, as a collection of coefficients. Suppose we know X explicitly. Whenever I say the word explicitly, by the way, I mean that I know it in a basis and I'm representing it in terms of numbers, so that it's like computational in nature, okay? So if I know X and I know T as matrices, question is, how do I determine Tx, okay? So what I need to do is to take T, and I need to apply it to X. But what is X? X is x1, x1 v1 plus all the way to xn vn. And this is going to be x1 t of v1 plus xn t of vn. This is using linearity of t. Okay, and then, okay, what I know is that t of v1 T of V1, what is it? Well, it's the first column of the matrix of T, right? It's A11 times W1. It's like this, A11 W1 plus all the way to AKJ WK. So this is going to be, so X1 times the sum of the first column, where I goes from 1 to k, okay, plus all the way to xn, same idea, ai n, wi, I is equal to 1 to k, okay? Okay, and then you see what if I want to figure out this quantity, what I need to do is to take this vector here, and write it in terms of the W basis. So the W basis has length k, so this will be a k by 1 column vector, because I'm in the basis gamma, which has length k. And what am I going to get? Well, I'm going to get, let me give an example. Let me give names to these coefficients. Let's say y1 up to yk, where what is y1? Well, it's the coefficient here of W1. So what am I going to get? I'm going to get x1 times A11. That's the only contribution from the first. And then each term will just have a W1 contribution. So I go all the way to xn A1n. And then you continue down there, yk is equal to x1 times AK1 all the way to xn AKN. Okay. Okay, so in other words, let's write this in a slightly nicer way. It's really x1 times this column. So it's a combination of the columns of the matrix. And these here are the columns of T beta gamma. These columns here. Okay, and finally, let's just, so at this point, so far everything is, I mean, you might get confused by the indices or whatever, but the idea is quite simple. The point is that T is represented by a matrix which has these entries A, I, J, and X is represented by a column matrix, X1 up to Xn. Okay, and the point, which is hopefully clear, is that when I apply T to X, the resulting vector can be expressed in terms of the data of T and the data of X. Okay, now this operation where we combine T and X and obtain the matrix of Tx, okay, has a name. It's called matrix multiplication of a matrix against a vector. So this is exactly how we define the matrix product between a k by n matrix and an n by 1 matrix. Okay, and yeah, and so the point is that if I just look at the above expression, the way that we define this product is so that this holds. And so the way that we get that is by saying that X1 basically is multiplying by this column. Okay, and each of the n numbers here, each one of them, let's say xj, that would multiply against the jth column of the matrix. And so the expression for matrix multiplication should be A1, should be exactly the coefficient here. The first coefficient here, the second coefficient there, and so on. So I'll get A11 x1 plus A12 x2 all the way to A1n xn as the first entry of the column matrix. And similarly down here, A1n x1 all the way to AKN xn. Oops. Sorry, what did I do? AK1 up to AKN xn. Okay, so the way you should think is that let's see how, yeah. So if we take a look at this, then we see that if we're interested in in a certain row, let's say that we're looking at row R. Oops. Row R. Okay, then row R will involve the corresponding row of this matrix and this column. Okay, so this I shouldn't yeah, sorry, I don't want to confuse by saying that this is a row. I mean, it is a row, but it's really just one element. So the rth entry. Okay, the rth entry here of the result comes about by taking all of these numbers and all of these numbers and doing basically a dot product, which means that you take the first times the first, the second times the second, the third times the third, and so on, and then you add those results together. So the formula for that would be exactly as written right here. Okay, so you have the YR. Okay, so this is giving you the first taste of matrix multiplication. It's saying that if you have an n by 1 column vector of numbers, and if you have a k by n matrix, then this represents a vector. This represents a linear map. And what we want is an operation which represents applying the linear map to the vector. And that operation, by this calculation, is exactly matrix multiplication defined this way. So you have two things. You have the abstract and you have the explicit. So let me just write that. So abstract x is taken to tx. This is in V. This is in W. Okay. And then explicit is that you have a column vector. Let me write it with brackets, which uses the basis beta. And what is it sent to? It's sent to matrix multiplication. Okay, like this. And this will give me the result of T of X. I'll just clean this up a little bit. Okay, so the abstract means that you don't make any choices of bases or anything, and you don't really know explicitly what these vectors are computationally. But then the explicit is really matrix multiplication of a k by n by an n by 1. And then we get a k by 1. Okay, and you see that the way that the indices are, the way the notation is developed is so that, if you have a k by n and an n by 1, the n disappears because this n is where the summation is over. You see here, I'm taking a sum over n values. And so that means that the fact that there's n of these a's and the fact that there's n of these x's, they combine together and they produce just a single number. So that's where this n that's why this n goes away and you just get k by 1. And similarly, in this notation, you see that because there's a beta here and a beta there, okay, that means that we no longer are going to need beta here because we're in W now, and beta is irrelevant for W. Beta is in the domain, gamma is in the codomain. Okay, now, so let me just continue. I know there will be questions about this, but let me go to step 4. Okay, and this is composing the linear maps. Okay, so this is full matrix multiplication. So in other words, it's multiplication of matrices with a multiplication of a matrix with a matrix, not a matrix with a vector. Okay, so the idea is very simple. We're going to introduce another vector space, U. So we have U, we have a linear map S going to V, and T is as before, it goes from V to W. So we know that that these can be composed, and the result annoyingly switches order. So it's S composed T because I apply S first and then T. And maybe the first thing to mention is that maybe I'll put it as a lemma, which is very easy to check, that if S and T are linear, so here what I'm assuming is that U, V, and W are finite dimensional vector spaces over the field, okay? And if S and T are linear maps, then their composite is also a linear map, okay? And that's not difficult to see. You know, if you want to check linearity, then you're gonna get this, right? So this is using the linearity of S. The linearity of S allows you to take S through the lambda and apply to you and distribute over the sum, right? Okay, but now what do I have? I have a number multiplied by a vector plus a vector, so I just use linearity of T. So this is going to be lambda T of S of U1 plus T of S of U2. And this is the definition of the composite. So here I'm using linearity of S. Here I'm using linearity of T. And here I'm using the definition of composition. So we see that that if you have two linear maps, their composite is linear. Okay, so as soon as we have this knowledge, okay, there's an obvious question, which is, suppose that I choose, so the main question that I'm going to answer right now is that if, let's say alpha beta and gamma, like beta, remember what beta was. Beta was V1 up to Vn, and gamma was W1 up to Wk, are bases for U, V, and W. Okay, and if, so S, therefore, so since I've chosen a basis, let me draw the basis in green. So there's a basis alpha for U, there's a basis beta for V, and there's a basis gamma for W, okay? And because I have this basis and this basis chosen, because alpha and beta are chosen, that means that I have a matrix for S. And because beta and gamma are chosen, I have a matrix for T. So let's say that S alpha beta and T beta gamma are the matrices of S and T. Then what is the matrix of S composed T? Okay, so actually, I'm just going to drop the composition, like, because it should be obvious when I put two linear maps together. When I put them next to each other, you should understand that there's a composition there. So people don't usually write the little circle. Okay, so what is the matrix of TS? Okay, so what do I mean by that question? Well, TS, it goes from U to W, and I know that I already have bases chosen. So that means that I should have a matrix for that thing. i.e., what is the matrix of TS, okay, in the bases alpha and gamma. Okay, so I give you explicitly what S is, and I give you explicitly what T is. What is the explicit value of T composed S? That's the question. Similar question as before. If I give you X explicitly, the vector, and if I give you the operator or the linear map explicitly, right? What is the explicit expression for the linear map applied to the vector? Same question here. Okay, and the way we do it is just by so what will it be? So TS, we just compute it. We can simply compute it. Okay, so what is this thing first? So alpha, beta. So this will be a matrix. Like this. And so how many columns will it have? Well, I mean, we have to apply it to the basis beta of oh, sorry, gamma. Should be gamma. So we have to apply it to the basis alpha, right? So there's m elements of the basis alpha, right? And each one of these basis elements, when I apply this linear map to it, I'm going to get a bunch of coefficients multiplied by the basis elements of gamma. So the number of columns is exactly the number of basis elements, the length of alpha. So it will be, and the number of rows will be the size of the basis gamma, because I'm going to expand the results in terms of the basis gamma. So because alpha has m elements and gamma has k elements, this will be a k by m matrix. Okay, and the columns are the expansion of TS of U J, the jth column, is the expansion of TS applied to the jth basis element. This, remember, this is the basis alpha, right? Alpha is the thing that is the U basis. Okay, and so we're going to take that U basis, Uj, we're going to apply TS to it, then we're going to expand it in terms of the gamma basis, which is the W's in gamma basis. So we just need to compute this. We just need to take TS, apply it to Uj, and write it as something times W1 plus something times W2 plus something WK. And these somethings, these things, they will be the jth column. Okay, so what are these? Well, I'm going to just do it as before. So this will be, so it will be T applied to what? So, well, okay, so here I'm going to need to know what S of Uj is. Okay, and actually, so what I should have done is given names to, 1 second, let me correct that here. So I need names for these things. So we already computed this. This was A11 up to K1, going up to A1N up to AKN. And this thing now needs I need a name for this matrix. So this is acting on the alpha basis, which has M elements. So I'll just give it the name B, B11. And how many rows will there be? It's the length of the basis beta. Beta has n elements, so this will be B1n. Oh, sorry, BN1. And this will go up to be, the number of columns is the size of the alpha basis, so that will be M, and that goes down to BNM. You just have to get used to this convention. There's one convention, we just keep using it again and again. Okay, so if we're given the explicit description of S, and we're given the explicit expression of T, okay, what is this thing? So this, let me write, we don't know what the answer is, but what kind of an object is it? It will be something that has M columns, because I'm applying it to M basis elements of alpha, and the number of rows will be the size of gamma, so gamma has K. So that means that I'm going to have some elements, C11 up to CK1, and C1M up to CKM. So we want to know, what are these elements? Okay, that's the problem. So sorry, I should have just given names to these matrices. So now I have done that. So this K by M matrix has entries like that. K by M matrix, K1, CKM, C1M. Okay. And the jth column, okay, is an expansion of this in a basis. So I've done that. So now I can, now I can work this out. So what is S of uj? Well, S of uj is going to be the jth column of this. So this will be the sum of B, let me use an index P, Pj, Vp. And this will go from P is equal to 1 to N, because I have N basis elements for N of the V's. Okay, so here what we see right here is the jth column of the S matrix. Okay, and now I'm going to apply T to all of this stuff. So this will be given by so I'm going to use linearity of T. So this will be sum of P equals 1 to N, B Pj, okay, T of Vp. And okay, and therefore, let me just copy this. And this T of Vp, right? I need to use the matrix of T. So the matrix of T is like this. I'm applying it to the pth basis element in beta. And so I'm going to get the pth column of T, which is just a bunch of A's. So this will be the sum of A in the pth column. And I'll use, I as a summation. And I'm summing over the basis for the final codomain, which is from 1 to k. And what? Oh, sorry. And what is this? So T of VP is expanded in terms of the basis. The final basis has a name, which is WI. Okay. So it's important to get used to these indices, but the important thing should be clear. So, which is this, that when I try to figure out the matrix entries of TS, what's going to come in? The A's and the B's are going to appear, because the A's are the matrix of T and the B's are the matrix of S. So of course they're going to have to appear in the answer. So here they are. Okay. And let me just rewrite this in a more standard way. So I want to write it as a sum from I is equal to 1 to k of something times WK, right? And then I will know, because of the fact that I'm, let me draw this in blue, because I'm applying TS to UJ, and because I'm expanding the result in terms of WK, right? This coefficient here will be exactly what you get by, in the kth row and the jth column of the answer. And what is that? Well, if I just look at this expression, right, the coefficient of WK, that's for K, the coefficient of WK, oh, sorry, I shouldn't have been using I from 1 to k. No, that's okay. It's WI, sorry. WI. So, yeah, sorry. That's what was screwing me up. Okay, so the way that you figure out the IJ and matrix entry of any linear map, as we discussed before, is to apply the linear map to a basis element, UJ, and expand that in terms of the WI, and then this coefficient is exactly Cij. And so what is this Cij? Well, we just have to take a look. It's a sum from P equals 1 to N of AIP BPJ. So this expression is the answer to my question. And what we see, we can think of it like this, that we have the A's. We have the B's. This is all a little bit too big. And what we're going to get is the C's. Where Cij is equal to what? So it's it's exactly, so this is the, oops, sorry, Cij. Ij represents the row and column. Okay, and the point is that this Cij, this number, which which is, let me say, it's in the ith row. Oops, I just want to draw this so that it's in the ith row and the jth column. So this is the ith row and the jth column. And what is it? Well, you can see that it's given by a sum of entries of A, which lie in the ith row, and the entries of B, which lie in the jth column. So that means that what you need to do is to take, actually, I'll just draw one picture so that it summarizes everything. That'll be useful. Oh, for God's sake. So I need to find the ith row here, and I need to find the jth column here. And this entry here is Cij. Okay, so in order to determine the Cij entry of the result, okay, you need to look at the ith row of A, the jth column of B, and you need to do their dot product. Essentially, this, for God's sake, this element times this element plus this element times this element, right? And you go down like that. So if we take, just to emphasize it even more, if I take the ith row and the jth column and multiply them like this, do their dot product, AI2, B2J, and this is just multiplication in the field. So I'm just adding and multiplying numbers now. I and J are fixed because I'm only interested in one particular matrix element, all the way to A I N B N J. And all this is equal to Cij. Okay. So right. So the idea, again, so just completing it, is that if you have a linear map and you describe it explicitly, and you have another linear map which you describe explicitly, and if you're using the same basis in the middle, right? So the important thing here is that when I'm describing T and when I'm describing S, I'm using the same basis, beta. Then in order to figure out the composition, you do a matrix, you do this operation, and this is the definition of matrix multiplication. This diagram exactly is the definition of matrix multiplication. You take an m by n and an n by k, and you get an m by k as a result. And so with this definition, it is true that, Ts alpha gamma is equal to T beta gamma S beta alpha, where this multiplication is matrix multiplication. And this multiplication, this is composition. So composition of linear maps corresponds exactly to matrix multiplication. Okay, and we end up with, yeah, so that's the kind of importance of matrix multiplication. And yeah, so you should get used to this. So now we've introduced a kind of new type of algebra where you can have matrices being multiplied against matrices. And the application of a matrix to a vector is just a special case where the matrix is just happens to be n by 1. Okay, but it's still a matrix multiplied by a matrix to get this. So this is totally consistent with part 4. Okay, so there's this calculus of multiplications of matrices is very important, and you need to know how to do it. Okay, I'll leave it there and start taking questions, but I'll of course be here for an hour taking questions. So
Okay.
people who have who have to leave, please raise your hand first here. If there's anyone who has to leave, can you indicate somehow if you have to leave early?
Okay, so Sina has a question.
Yeah, go ahead.
Hi, I had a question. So if you go down, like scroll down, please. Scroll down, like last page, the last page you wrote.
Okay, yeah.
Why is it CM1? Shouldn't it be CK1? Like in the matrix.
No.
Is it?
So what this matrix is representing a map that goes from where to where? It goes from U to W. Yes?
Yes.
Okay, so that means that the columns of the matrix, okay, are going to be what happens when you apply STS, when you apply this linear map to the basis alpha. So alpha is U1 up to UM. So first we apply TS to U1. Then we put the result in the column. But what is the first column? Okay, it's basically the result of TS applied to U1 expanded in terms of the basis gamma. And gamma has K elements. So that means that when we take TS and apply it to an element in U, the result is going to have the number of coefficients of that column, the number of entries in that column, will be exactly the number of the length of this basis. So it should be K. There should go from 1 to K.
Okay, thank you.
Oh yeah, sorry. So you're right. What? Sorry, I'm just. Sorry, I was trying to be careful, but somehow I screwed it up. 1 second. Yeah. Okay. Oh dear, what did I do? S and T. E1.
I think you mixed up the columns. Like we have to switch.
Oh yeah, sorry, I wrote this one wrong. Sorry. Sorry. Thank you for the correction.
Okay, thank you.
So A is going from, so this A should be K1. And this should be K1. And this should be the same, K1 to, so it should be K columns, sorry, K rows. And that's good.
And the second matrix should be from 1, 1 to NM.
BNM. Oh my goodness. I can't believe I did this. Usually I really tried to be exact, but okay. So then let's make sure that everything else is right. So this is a K by N matrix. This is an N by M matrix. And this is a K by M matrix, which is good. And then here I have A1 IN. Oh yeah, that's fine. Okay, everything else is right. I just, when I copied the matrices down, A and B were incorrect. But basically, yeah, so the number, you can always think, if you think about the dimensions of the spaces, then you should be able to check. And that's, yeah, thank you for the correction.
Okay, so Long Tai has a question.
Yeah, so I look over the textbook about fundamental theorem of linear maths, and
Yeah.
I understand the whole like proof, but my only problem is like
you don't, or you do
I
understand?
do.
Okay.
Yeah, so like I need your help with like understanding, like just provide some intuitions or another way to look at it, because I don't see any like correlations between the dimension of null t and dimension of range t. Like I know it's
Yeah.
right. And
We're going to do that in great detail next week.
Mhm.
But you know, maybe I'll just give you a quick preview. So so the basic idea is that, you know, when you have you know, the basic idea is something like this, that if you have V and W and you have a linear map from one to the other, okay, there will be so there's a special point in W0, okay, and there's going to be potentially some vectors in V that are sent to 0 by this linear map, right? And the set of vectors in V that are sent to 0, the important thing about them is they form a subspace, which is called the null space of T. So the null space of T is the linear subspace of V consisting of vectors sent to 0. Okay, so in other words, there's going to be a large subspace. Sorry, I don't mean a large subspace. There will be a subspace. It could be just 0, or it could be the whole space, whatever, depending on T, which will be sent to 0. So it's going to be collapsed, completely collapsed. Okay, so I'll draw them like this. Like there's going to be some subspace passing through 0. And this subspace, which I'll call null T, is going to be sent to 0. Okay, so you could think of it as like a level set in a way, like you know, the way that you normally study level sets of functions. This is a little bit different. This is a dimension from, sorry, this is a function, a linear map from an n-dimensional space to a k-dimensional space. So it's almost like you have k functions on this space, and you're looking at the 0 set of all k of them. You're trying to figure out which vectors are sent to 0 by this linear map. That's the null space. Okay, but there will be other vectors, okay, which I mean, I drew it as if it's perpendicular, but we don't have perpendicularity. So we have all these other vectors, right, which are not in the null space. So think about, okay, so whenever you have a linear map, there's two important subspaces that you can define from it, and one of them I just did. It's the null space. The other important subspace is the results, all possible results. So you could look at, you could say, if I apply t to every possible vector, what am I going to get in W? Is it going to fill up all of W? Not necessarily, right? It could be that this map T is just the zero map. So it could be that the image of this map or the range of this map might just be zero, or it might be some other smaller subspace. Okay, and let me draw it here. So this I'll write as the range of T, or sometimes called the image of T. Okay, so this red space and this green space, whenever you have a linear map between two vector spaces, automatically you will have the red null space and the green image, or range of T. Okay. Okay, so now what about the stuff that's not in the null space? All this stuff, where will it be sent? Well, okay, you tell me. If I take a point, where will it be sent?
The range, but
It'll definitely be sent to the range, right? We can agree on that.
not zero. Not to the zero. Right?
Not to zero. Yeah, if you take something out here which doesn't lie in the null space, it will be sent somewhere in the green space. Okay. Now the question is that map you know, is that map you know, what is the behavior of that map? So for example, suppose if I take two vectors, like one here and one here, okay? Neither of them is in the null space, right? But if I send them each to the range, it might happen that they are sent to the same point. Okay, it might be that these two different vectors are sent to the same point. There's no reason why the linear map should be injective. Okay, so why would that happen? The reason it would happen is that there might be a vector in the null space, which is the difference, happens to be the difference between those two vectors. So what we have here is, like with this triangle, is we have two vectors. They're not in the null space, but the difference between them is in the null space. And if that happens, that means that when I apply the linear map applied to this vector will give you a certain vector. And if I apply it to this vector, this vector is the same. You could think of it this way, that this one, let me call it, let me call this one U1 or V1. And let me call this one V2. And let me call this one N, let's say. So if V1 is V2 plus N, and if I apply T to V1, what am I going to get? I'm going to get T of V1 is equal to T of V2 plus T of N. But this is 0 because the N is in the null space. So you see that if you have two vectors which differ by something in the null space, then they're going to be treated the same way by T. T is not going to know the difference between them because T doesn't know anything about this null space. Everything in the null space is just sent to 0. So for all intents and purposes, it's the same value as 0. Okay, so what does that tell you? That tells you that if I want to understand this image, right? You could say the following, that this linear map, okay, you see, like this linear map, it establishes a relationship between the left-hand side and the right-hand side. And what you're tempted to do is to say that this image is just the same thing as the vectors which are not in the null space. Like if you have vectors in the null space, then they are sent to this green subspace, the range. And maybe the green and the blue are exactly the same. So that instead of studying the image, I could just study this blue stuff because it's not in the null space. The problem is that the map T is not an injection. It has this problem, okay? So what the fundamental theorem of linear algebra is saying is that in order to understand green, in order to understand the range, what you need to do is you need to produce an equivalence relation on these blue vectors. You need to say that two of these vectors in V are equivalent if we consider them to be equivalent when they differ by something in the null space. And if they differ by something in the null space, then they represent the same point in the range. So in the end, what you end up with is this idea that the range is equivalent to, can be represented by the equivalence classes of vectors in V, where we consider two vectors to be equivalent when they differ by something in the null space. So in other words, the image of T is the same thing, is equivalent to, or what we call isomorphic to, okay, to the equivalence classes where V1 is considered to be equivalent to V2 if V2 minus V1 is in the null space. So this I'll call, it is an equivalence class defined using T. Okay, so think of it like this, that we have some big space like this, V, and imagine that we have a linear map that looks like this. Imagine we have a linear map to a two-dimensional space, which I'll call W. And imagine that the entire thing is going to be mapped to a single line. This is the image of T. Okay, so just imagine that every vector here is going to be sent to something in this one-dimensional subspace, right? So if this three-dimensional space is being sent to this one-dimensional subspace, then the reason, the way that it's working is that there must be a large null space. So it could be, for example, that all this is the null space. So the vector, let's say 1, 0, 0, and 0, 0, 1 are both sent to 0. Okay, so the entire xy plane is sent to 0. But this vector, 0, 0, 1, is sent to this vector, which is, let's say, 0, 1. Okay, so what's happening is that the three-dimensional space is being collapsed to a single one-dimensional space. Okay, and so what would the matrix look like for this? Well, it would have to be a 2x3 matrix, because there's 3 basis elements for the domain and 2 basis elements for the codomain. Let's say if I had basis elements like this and like this. Okay, and where is 1, 0, 0 sent? It's sent to 0. Where is 0, 0? Oh, sorry. This is 0, 1, 0. 0, 1, 0 is sent to 0, but 0, 0, 1 is sent to 0, 1. So this would be a 2x3 matrix, like this. And you can even see what the null space is. You can see that the first basis element is sent to 0, and the second basis element is sent to 0. So the span of the first 2 basis elements are the null space. Okay, and basically we say that 2 vectors would be equivalent if they're at the same height. If they're at the same height, that means they differ by something in the null space. Okay, and they will be sent to the same point down here.
Yeah, that makes a lot of sense now. That's cool.
Okay.
Cool. Thank you.
You're welcome.
Look at it.
But anyway, we're going to go through this in great detail next week, so don't worry.
All right. So Omar has a question.
Hello, Professor.
Hi.
What's it called? Matrix multiplication it's associative, correct?
So you see here, see this? Matrix multiplication. What is it really? Really what it is composition.
And composition is associative. So
Yeah.
all right.
But because of the fact that that
So,
composition is associative, we know right away, without even having to check it, that this thing must be associative.
so I can apply S to X and then T to X, or I can just apply T to S and then all that to X, and we'll get the same results, right?
Yeah, what you're asking is this. Right, so the problem is, yeah, what you're asking is like this. If I take TS and you apply it to the column vector X, right, this would be the same thing as okay, so then I'm going to, so this is matrix multiplication inside there. So I'm supposed to multiply these, and then I'm supposed to multiply the result by X, right? But we know that if I use this, this sum, so let me start here. 1 is here. I have a matrix multiplication giving a matrix. Matrix and a vector. Okay, and I have another matrix multiplication right here. Right? So this is, I'm going to start the journey here. I'm going to use this equation, and I'm going to pass here to part 2. So I've expressed this as TS matrix multiplied by X. Okay, then I'm going to, then I'm going to use, this is the third step. I'm going to use star again, but on this multiplication, right? So I'm going to write it like this: TS applied to X gamma. This multiplied by that. So that's right. And then this is the TS applied to X. Yeah, and here I can expand this out. So this is T using the star again, but in a different way. I'm using associativity. Sorry. I'm using associativity of the composition. And then I can expand this out. And then I can, yeah. So then I can apply this like this: gamma beta, S beta alpha, X alpha. 4, 5, 6. So then 1 equals 6. This is the associativity. In other words, if I use the definition of matrix multiplication, the fact that I defined it so that it would be composition, and then if I use the fact that composition is associative, then I can associate, and then I can use the definition again. So this is, you could think that all of this is using the definition of matrix multiplication. This is using associativity, and then this is using definition back again to get back to a matrix. And on here, on this side, we have explicit, and here we have abstract.
Thank you.
You're welcome.
Just like quick question.
Yeah.
I haven't gone through the readings yet, but based on what you've explained, does does range include 0 or no? I'm not sure. Based on,
Well, so what is range? What's the definition of range?
based on what you said, if I'm not mistaken, all the elements that the linear that the map maps to.
Yeah, everything you get as all possible
So
values.
it includes 0.
Why does it include 0?
Yeah, so it includes 0
Why? Why does it include 0?
because 0 is a value.
Why? Why is 0 a
Because
value?
because T maps to it.
But why does T map to 0? I mean, why? I mean, how do you know that 0 is a possible value for the linear map?
Because of the null space.
Well, but how do you know that the
Right?
null space is
If
not?
the null space exists.
Yeah, I mean, what if the null space is empty?
Then it doesn't map to 0. But then would it
Okay, so
be a subspace, right?
what are all? So if I give you, here's a vector space U and a vector space V. Okay, and I have a linear map from U to V. What's a vector that you always have in any vector space that you're guaranteed that will be present inside the vector space U? There's only one vector that is always
0.
available.
Yeah, 0.
Okay, and what
0.
happens if you apply the linear map to that vector?
You get 0.
So if you have T, oops, if we have T of 0,
Hey,
what is it? Well, T, I don't know what it is, but it's certainly equal to this. And this
which
is
is
by
equal to
linearity.
T0 plus 0. Yeah,
And then you can cancel out, and so you get T of 0 is 0. So 0 is definitely one of the values, and it's for this reason.
Yeah. I just because while you were explaining range, you omitted 0 values.
And I did not
So
omit.
for
No,
like
I didn't
your
omit.
explanation.
I didn't omit. Oh, I see what you're saying. Yeah. Well, no, don't be confused.
So yeah, I was a bit confused.
The reason yeah, I mean, the range is a linear subspace of the codomain. So important is that anytime you have a linear map from U to V, there are two natural subspaces, one of them called the null space or the kernel, and one of them called the range or the image. They just have different names because people, yeah, everyone wants to be different.
All right then.
I'm sorry.
Thank you.
It's a subspace. What am I talking about? Yeah, it's a subspace.
Have a nice weekend.
You too.
Okay, so Gurmanjot has a question.
Yeah, I was just wondering, like, you know how we define matrix multiplication now. So I was like since like we have we like express every element in like some vector space V as like a linear combination of like its bases, like with like the given coordinates or like coefficients. Can we not just express that in terms of like a basis matrix multiplied by like the coordinate vector, something like that? Like I assume that you can, right? Like because like since like
wait, just slow down
Okay,
and try to simplify your question. Think about it and try to simplify your question. What are you asking?
Can you express every element in some vector space as the product of the basis matrix of
what is a basis matrix? What's a basis?
I suppose like with the bases in the columns or rows, something like that. I'm trying to, you know what? Let me just think about it for a second. I'm sorry.
Yeah, think about it. Yeah.
Okay. I'm sorry. Okay, thank you.
All right, so Isaac, you have a question?
Yeah, I just want to make sure that my understanding of matrix is correct.
Okay.
Yeah, according to the reading, like I believe that matrix is something related to linear map and linear combination. Is that correct? Hello?
Okay, so.
Yeah, I just want to know that, like, so when we have like a matrix.
Here's step one of what I talked about.
Yeah.
And I spoke about it also on Tuesday. Okay, now just wait 1 second.
Yeah.
Okay, so you're asking me, I mean, you have to understand the reason that I'm going to make a big deal out of it is because you're asking me whether there's any connection between linear maps and matrices. So, of course there
like,
is.
Yeah, I know.
Okay, so the purpose of a matrix is literally to represent a linear map.
Yes.
Okay.
And sorry to interrupt. My real question is that, like, is a matrix a relationship between, like, suppose we transfer like gamma to beta, so suppose we map gamma to beta, is a matrix about beta and beta only. Like, there's not really like much of gamma involved. You just like
Wrong. It's not. That's not right. Okay. Look at what's happening here. So this is just 1 second. So this is a this is linear map from V to W. Okay. V and W are different abstract vector spaces. They just are over the same field. Okay. So this could have dimension n, and this could have dimension k, and they could be completely separate vector spaces.
Yes, but
just 1 second, please.
Yeah,
please be quiet. Sorry. So I'm answering. Whenever I answer someone's question, it's not just for them. You know, there's many people listening. So I'm going to use the opportunity to make sure that everyone is on the same page.
Yeah.
So just wait. So we're mapping from V to W, and V has these elementary, important like basis that we've chosen. Okay, so we have these special vectors v1 up to vn that we chose because they generate v. They are a basis for v. Anything in v can be expressed in terms of these n vectors. Okay, so if we want to know what t is, what this map is, all we need to know is where does it take v1, where does it take v2, and so on. Where does it take vn? What happens when we evaluate t on these basis elements? Okay, now that's clear. So you understand why it's important to know the value of t on these basis elements.
Yes.
Okay, now how do I tell you the information of t of v1, right? If I take t and I say, I'm going to tell you what the value of t is on v5, right? How am I going to transmit that information to you? Well, okay, so t of v5 is an element in W. Okay, so if I just tell you, oh, it's t of v5 is a vector in W, you're going to answer and say, well, which vector is it? Which vector in W is t of v5? It's equal to what? Okay, and my problem is that in order to tell you, in order to give you the information, you need to tell me first which basis you prefer in W. If you have a preferred basis, like gamma, then what I can do is I can expand this out as something times W1 plus something times WK, and I can transmit to you these numbers, a list of K numbers. Those K numbers are what's happening in the columns here, right? T of V1 is represented by these numbers. What do these numbers mean? These numbers are the components. They're the coefficients of TV in the W basis, right? If I did not have the basis for W, I wouldn't be able to transmit you the correct type of information. And it depends on which basis you prefer for W.
Yes, I get that. So TV5 is something in W, and like everything else is something in, gamma. So the matrix is gamma about gamma, right? That's what I meant.
The matrix is what?
Like, say the basis is like a gamma.
So
the W1.
Can you see what I'm writing? Can you see this page?
Yeah. Okay. I know,
So do you see that beta is the basis for V and gamma is the basis for W?
Yes.
Okay.
Yeah. Just I want to be clear that TV5 is something in gamma, right?
No.
Like in the span
no,
of
it is
gamma.
not in gamma. It's something. It's a vector in W, and it will
so
be
it's in the
some
span
combination.
Of gamma.
It will be some combination of the vectors in gamma.
So that will be
which
the
combination?
span of gamma.
It will be in the span of gamma because the span of gamma is W.
Yeah. Yeah. So this matrix is something gamma about gamma. So we try
I don't
to
understand
show.
what you're saying. It's something gamma about gamma. I don't understand what that means.
I mean, just like a row is gamma, row is something in gamma, and the column is also something in gamma.
No,
like you
the rows in the
represent.
column. Listen. You are thinking right now at a certain resolution. Okay, you need to increase the resolution. You need to go from 1080p to 4K. You're too wild. Okay, so it's part of the training. The entries of this matrix are numbers in the field. That's what they are.
Yeah, yes, but I just want to make sure that this matrix represents the relationship of gamma to gamma.
Gamma
Like-
to gamma.
Like
Gamma to
something
gamma.
like I'm not sure how to express this right. Like the basis of W and the relationship to the basis of W. This matrix represents.
The basis of W. And do you mean the
Yeah.
basis of V?
No, I like that's why I mean this matrix has nothing to do with V. It's just like the exchange of.
You need to think about this again because you are I'm not sure what it is, but you're pushing hard and fast, and you need to slow down and increase the resolution. Okay.
Yeah, but this
So
matrix,
just think about it. Think about the following. I'm going to say it. I'm going to draw a picture. Okay. Which
yeah.
hopefully will help. But in order for it to help, you need to be quiet. Okay. Just 1 second. Okay. Now, let me change the drawing 1 second. Suppose that I have a vector space U, and suppose I have a vector space V. Okay. Now, every vector space has a special element in it, which is 0. Okay. Now, there are no other special elements. However, we can pick a basis. Okay, so I'm going to pick a basis. I'll call this alpha 1 and alpha 2. And I'll call this beta 1 and beta 2. Okay, I have chosen bases. Okay, now I have a linear map, which someone gave me before. They just gave me the linear map. It's some kind of machine that maps vectors in U to vectors in V. Okay, and I want to transmit the information. I want to compute this linear map in a computer, right? So how am I going to do it? Well, I need to know how any vector is sent by T. Where is this sent? Okay, that's the question. So, okay, but let me try to be as efficient as possible. This vector is a combination of the bases. So if I know where the basis is sent, that will suffice. That will be enough information in order to figure out what the value of TV is for any V. Right? So if I want to know the value of T on V, okay, I can forget about that problem and just do a preliminary problem and ask, before I figure out what it does to V, let me just figure out what it does to alpha 1 and to alpha 2. Okay, so what does it do to alpha 1? Well, okay, it really depends on what T is. Okay, I'm going to give you an example. So suppose that T sends alpha 1 to this, to this vector. T, actually, I'm just going to change the color of these for a second. 1 second. Okay, and so let's say that T of alpha 1 is this vector, and let's say that T of alpha 2 is this vector. Okay, why these vectors? Well, it's because the person who gave me the linear map, they are the ones who figured out this factory, okay, and that's what it does to these two particular vectors. Why am I applying why am I applying T to these two particular vectors? Well, just because this is a basis and that's going to be useful for me. because if I know the value on a basis, I'm going to be able to figure out everything I want to know. Okay. Is there anything special about this basis? No. You could have chosen any basis at all and do this. Okay. Now, what am I going to do? Well, I can see that T of alpha 1 is not exactly one of the betas, but it's some kind of combination of the betas. So I need to split it up. I need to write it as a linear combination. I can write T of alpha 1 is A beta 1 plus C beta 2. Okay, so that means that the value of T on this basis vector, okay, I'm going to represent it by these two numbers, A and C, because they tell me the coefficients of the result in the basis that I chose. Okay, the basis is like your framework for writing numerical results. So that A and C will go in the first column. Okay, now I do the same thing for T of alpha 2. T of alpha 2 is going to have a component along beta 2, and it's going to have a component along beta 1. Okay, let me call those B and D. It's really just like a multiple of beta 2. So let me write it as an equation. T of alpha 2 is some constant times beta 1 plus some constant times beta 2. And those constants, whatever they are, and they depend on T, they're going to go in the matrix as the second column, because that's what happens to the second basis, B and D. Okay, so the way that I figure out the matrix of a linear map is by applying the linear map to a basis. That basis was chosen. But the result needs to be expressed in terms of a second basis, the basis of the codomain. So you need two bases in order to write a linear map as a matrix. That's why in the notation must depend on T, alpha, and beta. It depends on the linear map, the first basis, and the second basis.
Yes, yeah, I see. And the matrix basically just trying to like, supposedly like something is mapped from alpha to beta, and we're just trying to where the alpha is mapped in terms of beta.
Yes, correct.
Yeah, okay.
Okay, so
What, I don't get a thank you for that long explanation? Tolerating.
Say thanks. I say thanks. Maybe just
Okay.
like the mic is like.
Okay, you're welcome.
So I really say thanks. Sorry if you didn't hear it. Sorry, probably
All
the
right.
mic. Sorry.
No problem. I'm just joking.
All right, so Gurmanjot has a question.
I thought about it. So I was thinking about what I was thinking about was, you know how you can express the basis as like, you know, a list of vectors like in V, right? So like, you know how you're mentioning like that notation for like the dot product or like for matrix multiplication. So like
For
what
matrix
if you
multiplication,
had matrix multiplication. So could you say that every x in V can be represented as its coordinates like in the basis of beta, like let's call these coordinates like, you know, the beta x with the beta x notation, and you can express it as the like the matrix multiplication of beta, like the list of vectors beta with beta x.
So here, you know, when we have a single vector in V and we have a basis chosen for V, right? Then we can, you know, this notation tells you to write the column vector with the coefficients. And then, you know, what I'm trying to say is that, you know, when you have a linear transformation that is applied to a vector, then in the matrix world, in the explicit world, that corresponds to matrix multiplication of this matrix on this column matrix.
Okay, yeah, I understand that, but like,
Yeah.
is there a way to not bring those two worlds, I guess, like together? Like
Which two
you know
worlds?
how
What two worlds are you talking about?
like what like you know how you're talking about like the matrices representing these linear maps
Yeah.
and bases
So
and
so
stuff.
what I was saying earlier is that the fancy way of thinking is written in green here. Okay, any vector, you could think of it as a linear map, actually.
Yes. Okay.
A linear map going from the field to the vector space.
Mhm.
Because how would you give a map from the field to a vector space? You just need to say where one is sent, and then you would know where every other number is sent by linearity. So a map from the field into a vector space is nothing but a vector in the vector space. Okay, and so when you take this linear map, I feel like your mind is blown or something. What's going on?
No, I understand like the concept like behind this, but like I was wondering
Do
if
you understand the fact that a vector in a vector space can actually
be a linear
be viewed as a linear map from the field
Yes.
to the vector space? Okay.
I can understand.
So if I have a map from the field to the vector space, and then I have a linear map from V to W, right? Then look, if I compose them, what do I get? I get a map from the field to W.
Okay.
Right? And so that will be TX.
Okay. All right. Like, okay, I understand that, but like my like what I was trying to get at was more like, you know how you can express x as x1 v1 plus all the way to xn vn, right?
Yes.
Can't you just express that as like the coordinate vector, like column vector beta x in multiplied by like the list beta. So like
Oh, I
that,
see. I see.
Yeah,
I see what you're
like
saying.
that. Yeah.
Okay.
Or like would that be
Just 1
useful
second.
notation?
Just 1 second.
Okay.
Okay. Yeah, I know what you're talking about. Okay, so what you're talking about is all contained in expressions like this. Okay, so you see here what I have is x1 up to xn multiplied by these vectors. TV1 is actually a vector, right? Whereas x1 is an element of the field. So this is you could think of this, some people would write this as like x1 up to xn times TV1 and TVN. So in other words, they start mixing matrices by they start to put vectors in the matrix rather than just numbers.
Yeah.
That's what you're fishing for. Okay.
Yeah, that's what I'm thinking.
That is you can do that, but you're not gonna, you're not going to get anything that you can't get with this, first of all.
It's
unnecessarily confusing. And it's not, let's put it this way. The important thing for you to understand by an order of magnitude is what I'm explaining here. It's the way of representing linear maps and vectors in terms of matrices and column vectors and explicit elements of the field. That is the thing that you need to understand. The other stuff I would say is potentially notational convenience, but it's not getting you anywhere.
Okay.
So there is a context where you might want to take matrices of vectors, matrices of other more fancy things. Okay, but that is not going to help for anything in this course or the next course or any course that I'm aware of. But there is a certain context in higher math where that formalism is worth developing. It is not used here. Okay.
Sorry, I just wanted to know if that was possible.
You can make a vector, you can make a matrix with all kinds of stuff in it. You can put vectors in a matrix besides numbers. You can put, algebras in a matrix. You could do all kinds of interesting things in higher, by generalizing the idea of a matrix. I mean, what is a matrix? Actually, what is a matrix? It's just a, we talked about lists, right? A list, right, is something like, it's an ordered, it's like a tuple, like it's an ordered list. I mean, it's a different kind of data structure than a set, right? We discussed what a list is. So it's, if you want, you could say that a list is really a map from the natural numbers into a set X. So a list of elements, or let me put it this way. I don't want to get anyone confused. I just, you're fishing around for something. And so let me just explain what you're fishing around for. So a list of length n is a map from Bn to X. If you have a list of length n of elements in X, you could think of that list as being a map from the standard set of n elements to X. Remember that this is just 1, 2, up to n, right? So if you know where 1, 2, 3, 4, and so on are sent, that will give you a list of elements inside X, right? So a matrix, an n by, let's say a k by n matrix, what is that? It's just a map from bk cross bn into X. And that makes sense for any set X. Okay? But the way that we're using it is just to map it to the field. So that is the useful concept that we are using in linear algebra. But of course, in general, you can consider lists of other things, right? Like, what are we considering lists of? We're considering lists of vectors or lists of numbers. And so what we're considering is lists of double lists, if you want, which are called matrices.
Like lists of lists? Would that be a
well,
useful
you could think of it that way if you want, but that's not what I said. I said it's a list which is a double, meaning that it's from bk cross bn, the Cartesian product of bk with bn into f. Now, of course, if you can always, any such map like this, you could think of it as a map from bk to, anyway, I don't want to get into deep waters.
Okay, wait, so the basic idea is that essentially like any element in a vector space can be mapped to, like any element in a finite dimensional vector space can be mapped to a list of of some length, right? Can be mapped with this context.
So we are representing vectors as lists of numbers, and we are representing linear maps as double lists of numbers. Okay, and the important concept is not make lists of everything, make double lists of everything. That's not the concept. The concept is to represent abstraction in terms of lists of numbers. That's the computational concept, okay? That's the reason why I'm saying you can do all kinds of things by putting other things inside lists and putting it in double lists and matrices and all that stuff. But that's a completely separate idea from the one that I'm trying to push here.
Okay, all right. Thank you.
You're welcome. We're getting up to time, so and there's no hands up, so I'm going to take this opportunity to finish. Yeah, let's have a good weekend, and if there's some parts of the there's maybe 1 or 2 questions which I'm aware they don't they use a couple of concepts which are in the reading which are not in lecture, and so if you want to ask for clarification about those readings, you can do so on Piazza or in your tutorials. But if you do the reading, you should be good. Okay, have a good weekend. Thanks a lot, Syed.